In this video, we will be talking about percent yield. Not every reaction completely reacts, or mistakes can be made in a laboratory to keep a reaction from completely reacting. For these reasons, we can calculate percent yield. Some important definitions to know for percent yield are actual yield and theoretical yield. Actual yield is the actual amount of product being produced in lab. Theoretical yield is the amount of product calculated on paper. This would be your ideal amount if the reaction went to 100% completion. Percent yield indicates the efficiency of a reaction and theoretically cannot go over 100%. We calculate percent yield by dividing the actual yield by the theoretical yield. And to get to 100%, we multiply this by 100. The actual yield will be what's given to you, and the theoretical yield will be something that you must calculate using stoichiometry. Let's do an example problem. So, balance the below equation for the combustion of butane. So pause this video and try to balance this yourself. You should have gotten 2, 13, 8, and 10. Theoretically, how many moles of water will be produced if 8.75 moles of butane are used? So the first thing you do is you start with your known, which is 8.75 moles of butane. And you use the molar ratio to get to the moles of your unknown. So we do moles of known on bottom, which is 2 moles of butane, and moles of unknown on top, which is 10 moles of water. So now I'll multiply the top and divide by the bottom, and I should get 43.8 moles of water. Now, what is the percent yield if 42.6 moles of water is actually produced in lab? So here I have the theoretical, and now it's saying that 42.6 moles of water is actually produced. So in order to find percent yield, we divide actual yield by theoretical yield. So here, my actual yield is 42.6 moles of water, and I divide that by my theoretical yield, which we found was 43.8 moles of water, and I multiply this by 100, and I get 97.3% yield. Example 2. Balance the below equation of the synthesis of nitrogen and hydrogen to produce ammonia. Pause this video and try balancing yourself. You should have gotten 1, 3, 2. Part A asks if 8.4 grams of hydrogen are used, theoretically, how many grams of ammonia should be produced. So here I'm given 8.4 grams of hydrogen, and I need to get to grams of ammonia. So I need to go from grams to moles, so I use the molar mass of hydrogen, which is 2.02 grams of hydrogen for every 1 mole of hydrogen. And next I need to go from moles of my known to moles of my unknown, so I'm going to use the molar ratio, and I have 3 moles of hydrogen for every 2 moles of ammonia. And now I need to go from moles of ammonia to grams of ammonia. So for every 1 mole of ammonia, there are 17.04 grams of ammonia. So now I multiply the top and divide by the bottom, and I should get 47 grams of ammonia being produced. Now it asks, calculate the percent yield if only 40.1 grams of ammonia were actually produced. So for percent yield, we do actual yield over theoretical yield. So here my actual yield was 40.1 grams, and my theoretical yield was 47 grams. I multiply this by 100, and I get 85.3% yield. Flip the paper over. Example 3. Use the data table 2 to complete the following questions. First, balance the decomposition reaction. Pause this video and try to balance yourself. You should have gotten 1, 1, 1. Using your beginning amount of copper 2 carbonate, how many grams of copper 2 oxide are theoretically produced? So for this equation, we have to find the starting amount of copper carbonate. The way we do that is we look up here at our data table and we see that we have the mass of copper 2 carbonate and we have the mass of the test tube before heating. So this would be our starting amount. But this is the entire mass with the test tube. So in order to get just the carbon 2 carbonate, I need to subtract 4.56 grams, which is the weight of the test tube, and I get 8.09 grams. So I know that my starting amount of copper 2 carbonate is 8.09 grams. Now I'm being asked to get 2 grams of copper oxide. So to go from grams of copper 2 carbonate to copper oxide, I first need to get to moles of copper 2 carbonate. So the first thing I do is get the molar mass of copper 2 carbonate, which is 123.55 grams per every 1 mole of copper 2 carbonate. And now I can get to the moles of my unknown by using the molar ratio. So I know for every 1 mole of copper 2 carbonate, there's also 1 mole of copper oxide. Now I need to get to grams of my unknown. So I use the molar mass of copper oxide, which is 79.55 grams of copper oxide for every 1 mole of copper oxide. And now I'm where I need to be. I've gotten what they asked me for, which was grams of copper oxide. So I multiply the top and divide by the bottom. And the answer I got is 5.21 grams of copper oxide. Now it says, according to your data, should say data, says date, how many grams of copper 2 oxide were actually produced? So to find how many were actually produced, I look at the data table and I see the mass of copper 2 oxide in the test tube after heating, so after the reaction is over, is 9.53 grams. Since this is the mass with copper 2 oxide in the test tube, I must subtract the weight of the test tube in order to get just copper 2 oxide. So 9.53 minus 4.56 grams is going to be 4.97 grams. So I did 9.53 grams minus 4.56 grams, and that should equal 4.97 grams of copper 2 oxide. Now that I know my actual yield and my theoretical yield, I can determine the percent yield of copper 2 oxide. Percent yield is equal to actual over theoretical. So my actual is what I got in the lab, which is 4.97 grams, over my theoretical, which is what I calculated, which up here is 5.21 grams. And I multiply this by 100, and I get 95.4% yield.